Hello, everyone. Welcome to the second session of Explore Machine Learning. This session will be focusing on neural networks, and we'll be expanding a bit of what we learned last session. And we will be looking at TensorFlow Playground a bit. So that's an easy beginner-friendly version of TensorFlow, which should be interesting. So yeah, thank you everyone for coming. And without further ado, let's start. So we'll be starting off with this little video. Hopefully the audio should work this time around.
Hi, I'm Nat.
And I'm Lo. And this is our 20% project, where we go find out about different Google stuff we're curious about.
Last year, we got to make a documentary about how voice search works. And that was the first time we heard about something called machine learning.
Since then, we've been kind of fascinated by it.
So today, we're talking with Greg and Chris to learn more about it. How would you describe machine learning to someone?
Well, there's a lot of problems it's really easy to solve with computers. Computers can go and simulate how galaxies move and how the courses of asteroids going and how close they're going to come to Earth. I could never hope to go and do that, but I can go and do this problem like recognizing that that's a tree, which is so much tremendously more difficult for a computer.
It doesn't feel like intelligence to us because it's so effortless as a human being to do it, but for a computer, it's actually really hard.
Because the real world is kind of messy and unpredictable at times. The strict logical rules that go into traditional programming just don't work.
Instead of going and writing programs that solve the problem, we write programs that learn to solve the problem from examples.
And it's this process of learning that allows them to improve over time and to actually be more clever than they would be if we wrote down a very rigid set of instructions for them to follow.
Machine learning is in so many different things that we use today that it's kind of like this invisible magic ingredient.
Phones with the ability to understand human speech.
Machine translation.
Everything from facial recognition.
Sorry, the video cut off for a bit. I'll try to pick up from the bit we were just at.
Machine learning is in so many different things that we use today that it's kind of like this invisible magic ingredient.
Phones with the ability to understand human speech.
Machine translation, email spam filters.
When you go to the ATM and you give a check and it can read the handwriting.
Or a Photos app that can automatically organize your photos based on the things that you like to take photos of. Like, here are all my mountain photos, here are all my food photos.
Here are all my dog photos.
Here are all my feet photos.
Everything from facial recognition to going and trying to recognize whether a particle is present in a particular collision at the LHC.
Which we would just like to take a time out to say is that big tube in the ground over in Europe that smashes particles together at really fast speeds so that scientists can use that information to unlock the mysteries of the universe, among other cool things. Now back to our episode, because I am getting really dizzy doing this. Whew. Whew.
So researchers and scientists are still experimenting and trying to find the best ways to teach computers how to learn. But a lot of the progress is coming from these algorithms that are based roughly on how the human brain works, and these are called artificial neural networks.
So an artificial neural network is something that it's a rough mathematical cartoon of how a biological neural network works. In a biological brain, we have individual cells called neurons. Each neuron looks at what its neighbors has to say and then decide what it wants to say. And in artificial neural networks, we have little mathematical functions. We put them in some organized structure, and then we say, okay, you guys all together, learn to do this task.
We have lots of neural nets that are really great at going and recognizing, this is a cat, this is a dog, this is a frog, this is a mouse, this is a horse, this is a truck, and things like that.
So take, for example, trying to recognize what this is.
So it used to be that we were really proud if we could get a neural net with 3 layers to work. And it's recently that we've made a lot of progress on techniques that allow us to train much deeper neural nets.
And that's why this kind of machine learning is also called deep learning. A neuron in the bottom layer is just going to be looking at a tiny piece of the picture and making some computations about it. It doesn't understand anything about dogs specifically.
But what the neuron does understand is it says, I'm giving a signal that's useful for somebody who's giving a signal, who's giving a signal, who's giving a signal, who's giving a signal.
They're kind of able to unfurl this really high-dimensional knot and pull it apart and make it easier to go and separate different things that are close together on the surface from things that were tangled all together earlier.
But then at the top, we'll put two neurons, and these neurons look at the whole picture so far.
They're basically experts at making the final call, figuring out, oh, all the layers below me said these things, so I know that this is a dog, or at least I'm 92.4% sure that it's a dog, so it's basically a dog.
And while there's been a whole lot of progress with teaching computers to learn, they're still much slower learners than we are, and they make mistakes that you and I wouldn't.
So what I was working on is sort of trying to find a way to go and look at a neural net and ask, what does the neural net think the platonic ideal of a cat is, or the platonic ideal of a dog, or anything it can classify as? And suddenly you can go and ask, neural net, what do you think a cat looks like? And you get a picture of a cat. Or, neural net, what do you think a barbell looks like? So these weights. And it goes and it shows you a picture not only of a barbell, but of an arm attached to a barbell. So the model thought that the arms, it only learned what barbells were from looking at pictures of barbells, and they're often held by muscular weightlifters. And so it learned that there was, barbells have arms attached to them.
It takes them a long time to learn. If you show it a picture of a school bus, when it's early in learning, the very next time you show it a picture of a school bus, it's only a little bit more likely to say school bus. It doesn't get it, even though that was the very last thing it saw. Whereas, you say to a kid, that's a filing cabinet. And then a second later you say, what's that? Yeah. He's not gonna be like, shoe, right?
Well, the more you describe this, the more I'm amazed by human beings.
Yeah.
The effect is like, wow, human beings are really amazing.
We're really amazing learning machines. Oh.
Right, so that video should have given a brief overview of neural networks and the sort of inspiration behind them from biological neural networks in our brains. And if you've ever read anything about machine learning, you may have come across the term neural network. They're a popular choice for machine learning models because of their ability to handle complex data and make accurate predictions. So it can handle complex data because of all those layers of computation, which simple models just fall short at. And that's what we're going to be exploring this week, how the different layers interact with each other in a neural network. So in short, a neural network is a mathematical function that maps given inputs to desired outputs. And in the last session, the introductory session, you learned about a couple types of machine learning models, such as classification, regression, etc. And simple models work fine with simple data. But as soon as you want to interpret complex data, like images or audio, or even numerical data, which has a lot of variables in it. So say, for example, house pricing. So house pricing, you need to account for location, number of bedrooms, size, and all those other variables. So you need to have a model that's well equipped to deal with that sort of complexity. And these simple models are connected together into layers. And this is where the idea of depth of deep learning comes in. So in reality, a neural network is a big, complex mathematical function that looks nothing like this diagram, but this diagram just serves to help you understand what's going on. So in reality, all those black dots are just mathematical functions taking in an input and spitting out an output only if it has to. And that's where the analogy to a brain comes from, because it works quite similar to a neuron. So like any other machine learning system, in a neural network, we will train our model with data, feed the data into the model, and it will attempt to make a prediction. So the first prediction will essentially be garbage because it hasn't had enough data to train with. But the feedback from that prediction will be used to improve the model. So, and we keep reiterating over this until our prediction quality is sufficient and the model is tested with new data, and it makes a prediction based on what it's learned from the training set it's comfortable with. So now what this diagram doesn't show is every neuron is able to learn and improve based on feedback. So now we're going to take a look at each individual neuron itself. So here's a rough schematic diagram of how an artificial neuron works. Um, Essentially, this flowchart says that, right, there's an input and we apply an activation function to it. So this activation function is a mathematical way of setting the threshold or condition for activating a neuron. So it's basically an if statement, if you've done programming before. So it's similar to saying if time is greater than 11 a.m., eat lunch. So stuff like that. It's you helping the computer make a decision. So what the neuron does is it sees if the input value it gets meets the activation function's requirements. And if it doesn't meet the activation function requirement, it doesn't do anything. It goes into the red box. Um, but if it does meet the activation function requirements, um, that means it has to do something to the data it got, and it should pass on the output from that to the next neuron. So going from layer to layer, selectively picking which bits of data you want to trickle down. So this operation is carried out across a lot of nodes in the network, allowing very complex patterns to be learned and predictions to be made. So we're going to take a look at a couple examples of artificial neurons and how they work, like individually. So in this one here, the number 5 is input into the neuron, and the neuron's activation function has learned to check if the number is less than 10. If the input passes this test and the neuron is activated, so 5 is less than 10, the neuron does get activated. So this is one of the simplest forms of neural network, and it's effectively the same as linear regression or fitting a line to the data, where it's a very simple parameter that you need to pass. Um, Another example of artificial neurons would be this one here, that is part of a computer system that's used to detect numbers. So say you input this digital image of a 7 um, into this neuron. So this neuron's activation function is it's learned to check if an image like this has curves or not. Um, so this input doesn't have curves because the 7 over here is composed of straight lines. Um, so it fails to pass the test. So this neuron doesn't get triggered. So this neuron stays off in the neural network model. However, this one is a scanned image of a 6. Now, in reality, the 6 will have a bit of curvature to it, but then because they scanned this digital image onto the schematic, it doesn't look like it has a curve. But since the number 6 does have a curve on it, the neural network, the input has a curve, so the neuron is not, uh, so neuron will get activated and pass on the information to the next neuron. And simple functions like these can combine to make more complex decisions. So for example, the ability of this neuron to determine whether or not the input has a curve is due to other neurons checking to see if a pixel is black or not. So the decisions made by each level of the neural network helps inform decisions in future networks. And over here, we're going to be looking at some of the common activation functions that modern neural networks use. So these are the ones used in industry. So first up, we have this function called the sigmoid function. And it essentially outputs a value between 0 and 1. And that's the shape of the function. It's used quite a bit in logistics and stuff to show a gradual change from 0 to 1, etc. And yeah, so that's the sigmoid function. This is how you calculate it, say on a calculator. Um, Here's another activation function called the rectified linear unit, or ReLU. So the ReLU activation function works quite quicker because all it does is computes the maximum of 0 and the input. So if you have a negative number input, the result's always 0. But if you have a positive number input, the result is that number itself. So I hadn't really seen this function before I looked at these slides, and apparently it's a fairly recent one that that is becoming more and more popular just because of how easy it is to compute compared to the sigmoid function. So yeah, researchers describe the field of machine learning less like engineering and more like scientific exploration. So going back to the sigmoid function, for a long time, the sigmoid function was used until the ReLU was discovered to be more efficient and effective for many situations. It's important to remember that it's not necessary to know all of the maths behind machine learning in order to use it, but it's shown here, we've shown the maths here to help reinforce the concept that machine learning is at its core a complex mathematical function that's trained to work well to reach a particular goal. So you don't need to thoroughly understand all of the maths. You just need to know that it plays an important role. So over here, we're going to look at a neural network for classifying whether an image has a dog in it or not. So neural networks can be composed of many hidden layers, and these are intermediate steps to get from the prediction to the output. For example, a neural network may have layers to detect certain colors and shapes, and other layers to differentiate between certain types of animals and breeds. It's important to clarify the neural network does not know what a cat or dog is. It's just learning to do what we want it to do based on feedback and the pattern it detects. So you might be thinking, how does a neural network learn from its feedback? So neural networks are loosely modeled of the biological brain, as you can probably tell from the name. So the connections between neurons can be strengthened and weakened using biases. So these curves connecting neurons to each other, we can increase and decrease their strength using weights and biases. So for example, when a dog receives a treat and a pat on its head for retrieving a ball, it's more likely to do that again. So it's the same idea as positive reinforcement. So weights and biases allow a neural network to learn what pathways work for certain tasks and bias the network to using those pathways over and over again. So if a neural network's trying out a bunch of paths and then it realizes, oh, making this connection rewards me more or is more correct, then I'll do this way more than making, say, disconnection or disconnection. So the neural network, so over here, the thicker paths indicate paths of greater weight, and the thinner paths indicate paths of like lesser weight. So weights and biases allow neural network to learn pathways, to learn what pathways work for certain tasks, and this makes the network more effective and efficient at making predictions. So all of these complex calculations are accomplished far more quickly and often more efficiently than a human could. It requires a lot of computing power to achieve high quality results, which is why neural networks were initially thought to be infeasible. So back in, I think around the 20th century, when they proposed these ideas of machine learning, they realized that, oh, we don't have the computing power to carry this off. But nowadays, data centers, including even cloud computing, um, gives processes the computing power they need to make neural networks a reality. And that's sort of why they're becoming so popular. So now over here, we're going to look at one of TensorFlow's. It's essentially a graphical version of TensorFlow called TensorFlow Playground, which where you can actually see the features, the neural networks, and the neurons interacting with each other and the result they give out. So if you hadn't heard, TensorFlow is you can think of it as a Python library um, developed by Google to help both hobbyists and industry professionals to develop neural networks and carry out machine learning. So over here, TensorFlow Playground is a variant of TensorFlow, or which you can just deploy and use without any coding. And we're going to be diving into this for the rest of the session. So machine learning is typically implemented using programming languages like Python, as I mentioned before, and R, which is the language used quite often in statistics. And specific libraries are pretty popular, like scikit, Theano, and TensorFlow. And these libraries just make your coding much easier. For those of you who do not know how to write code, there's this API offered to make machine learning an option, and that's TensorFlow Playground. And in this session, we're going to use TensorFlow Playground, a tool for exploring and learning about machine learning without having to write any code. So let's have a quick look at the different components of TensorFlow Playground. So over here, the most noticeable thing is output, and we get this weird graph shape here with orange and blue dots. So let's see what that means. So when you think of machine learning, you might be thinking of models to use, models that can detect whether, oh, this X-ray image is showing early signs of cancer or not. And while that is a good application of machine learning, it's quite advanced for our stage. So for now, we're going to try to find a neural network that's able to separate the blue dots and orange dots. In essence, come up with regions of the graph um, to mark as orange or blue, depending on with the with the data it already has. So so there are a few questions which we should think before we start coming up with a model for this. Firstly, what do you need in order to successfully separate the lines? So if you look at the output graph, it's quite a circular boundary between blue and orange in this case. So we'll have to pick our neurons. So over here we have some pre-built neurons and features, and we need to pick the right ones to essentially come up with this boundary. So while we can't come up with a circle, we could use several lines to just cordon off this middle section, and then we essentially have a model that separates blue from orange based on the given data. So that's one approach which we can try. And then if we look, I'll go back. If you look on the left, we have features. So in machine learning, features refers to the properties which you need to feed in to the model to allow it to run. So it's basically things to look out for. You can think of it as the input variables from the earlier example of neurons. So features are the information drawn from your data examples, which distinguish one example from another. In TensorFlow Playground, these are simply mathematical functions like vertical lines, horizontal lines, and their combinations. So we'll be looking at vertical and horizontal lines for the purposes of just using TensorFlow Playground in this session. But obviously, once we get to actual TensorFlow encoding, we can the sky's the limit, really. So um, going back to the idea of features in the real world, so say if we're trying to distinguish dogs from cats, some features we might look at are size, color, tail length. So those are the input variables we call features. Um, Say we wanted to classify handwritten numbers as we were doing earlier, features to look for would be the number of curves and the number of straight lines. Um, if we were coming up with a neural network that recommended videos, so a video recommendation algorithm, we could, some of the input variables would be video topic, number of views, creator of the video, and video users watched, just to name a few. And just as a last example, say you are coming up with a neural network to predict which ad to display to a user. So The features for that can include the user's query, so what the user was searching for in the first place, the type of device they're on, and say the time of day maybe. So again, features play an important role in our neural network because it decides what goes in. Now we're going to look at the middle section, which are the hidden layers, and this is essentially where the magic happens. So these hidden layers take in our input features and pass on information from one layer of neurons to the next. So, so it's in this region where the complex patterns in the data are discovered. So permutations of the feature data is tested on how well it separates the data. So the outcome is graded. This is known as loss. So we're going to be covering this concept of loss later on, but essentially, loss is loss is a measure of how well your model's doing. So the lower your loss, the better your model. Loss measures how different your model is from reality. So your predictions, how different they are from the data you've put into the model. So, and loss is used to grade the model. And then there are some rules of thumb for crafting neural networks, but it's not likely I could tell you before what the right answer is. So a high quality neural network is just experimentation and iteration. So it's more like an art where you can't come up with the right answer straight away. You need to look at how your model's currently doing and where it can be improved. So now there are some TensorFlow exercises that you guys can have a look at. But before we go into that, I'll try getting the model up on my screen just so I can play around with it for a bit. So just give me a quick second. Right, so what we've got here is, can everyone see the neural network up on my screen? Sweet. Okay, so what we've got here is essentially um, a neural network, the neural network I was talking about earlier. And these are the features. So what properties we want to feed in. These are the neurons. We can increase and decrease the number of neurons accordingly. We can increase and decrease the number of hidden layers. And yeah, so each layer has its own number of neurons. And the outputs are have mixed weights. So over here, the model's already been trained, and these are all the weights associated with each connection between neurons. Um, in the data column, you can mess around with the sort of data we want to use. So we'll start off with this example of a bunch of blue dots in the center and orange dots around it. And we're trying to differentiate blue from orange. Now, in the real world, blue and orange could be um, two different. So say an example that comes to mind is, say you have a telescope mapping out different bodies it sees in the sky. Um, so this could be the XY coordinates for the position, and then the training data says, oh, all the bodies orbiting this area is one kind of body. So say an asteroid maybe, and all the bodies in this area are associated with a planet. So that's one example of this data. Again, it's not what it represents, but it's just something I thought of. Um, so yeah, we're going to be using that input data. Ratio of training data to testing data is, as we mentioned before, whenever we get a data set, we split it into a training set and testing set, and we train it with the training set and then test it by comparing it with the testing set. Noise we've set to 0 just for an idealized scenario, and batch size we've set to 10, so number of batches. So when I hit play, we'll be running the neural network at this learning rate with this activation function. Um, so I talked about sigmoid and ReLU in the slides. Tan H is hyperbolic tan. So that's another mathematical function. Again, you don't need to know about it, but it's another function which has a similar shape to sigmoid. And then regularization rates we don't need to dive into at the moment. And the problem we've selected is classification. So classifying whether something is orange or blue given its position. So when I hit play, the things to look at is the test loss and the training loss. Again, loss is a measure of how good your model is. So you should just look at what happens to loss. And epoch over here is just a time counter. So if I hit play, you should be able to see that it came up with this model where, right, it established this boundary to separate orange from blue, and the loss was initially quite high, then it plummeted down, indicating our model just got better and better. So you see in this initial phase, there wasn't much change in the model, it wasn't improving much, but then after it's learned enough, it suddenly shows a great decrease in loss. Remember, lower loss is better, so it means our model is more fine-tuned with reality. So I'll let you guys have a play around with this soon because there's quite a few tasks in this which would be worth exploring. Something I'll show you is how we can compare, say, the sigmoid activation function with the ReLU function. So if we run the same model with sigmoid, loss fell down pretty quickly. So indicating sigmoid might have been a better idea than hyperbolic tan. But if you do the same thing with ReLU, reset it, ReLU actually took a bit longer in this case than the sigmoid did. So it's essentially coming up with a model, seeing what works best, and tweaking around with it. So if I just stop sharing and go back to the slides. Right. So this link here um, will take you to a neural network learning page. I'll drop it down into the chat. And then, so I've been told to spend approximately 20 minutes letting you explore the different tasks on the page. Given the time constraints, I'll probably just leave it to about 10 minutes, just so you get a rough idea. Again, the questions and answers are all available on the webpage, so you can feel free to explore it in your own free time. Oh, I just saw a question in the chat. Could you quickly overview what activation is? Yeah, sure. I'll just drop this link and then I'll talk about activation one more time. While I talk about that, feel free to explore this link here. Yeah, so activation. So I covered activation a bit early on, but it's essentially a quite simple idea. So as I mentioned, neural networks are made of layers, and each layer has neurons in it. So what a neuron does is it takes in an input, and then it decides whether or not to give out an output. So the activation function is what helps it decide. So it's essentially the same. If you've done any coding before, it's essentially the same idea as an if statement. So in programming, you can say if x greater than 0, print out hello world. So what that statement does is it looks at x's value, sees if x is greater than the value we said, so x greater than 0. So if x is a positive number, it prints out hello world. So that's essentially what the activation function does. It helps you decide whether the input value meets the function's requirements. So if it does meet the function's requirement, this neuron does get activated. It does whatever it's supposed to and passes on its output to the next neuron in the next layer. If the input doesn't meet the activation function, it doesn't activate the neuron. So I think, was it the previous slide? No, not this. So yeah, over here, where we had the example of the numbers, if the activation function here is less than 10, if 5 is lesser than 10, activate a neuron. So if 5 is lesser than 10, the neuron does get activated. A disactivation function looks for a curve, and while looking for a curve isn't a very straightforward mathematical operation, you got to realize that this neuron could be in a layer with a bunch of other layers before it, and it can use the information from those previous layers to decide whether or not this has a curve. And some of the common activation functions used in industry are the sigmoid function, and ReLU. So sigmoid function is something I'm quite familiar with. I've used it before in a couple models. It essentially gives an output between 0 and 1. The closer to 1 being the more likely you are to get activated. The ReLU function, on the other hand, is I had to research this earlier, but it's quite a recent one, and apparently it's used because it's quite faster than sigmoid in a few other cases. But again, that's not always true. As we went through that example on TensorFlow Playground, we saw that the ReLU function actually did worse than the sigmoid. But what ReLU does is it takes the maximum of 0 and the input. So what that means is if you put in a negative input, your output's always 0 because 0 is always bigger. If you put in a positive input, your output is that input itself. So that's what gives the ReLU function its shape. I hope that answered your question about activation functions. Great. So yeah, I'll let you guys have a few more minutes to play around in the neural network playground exercises. You can feel free to skip to the ones that look interesting to you, because you can always work through them whenever you get the time. And the answers are all included in the slides as well. It's just a really good exercise to look at how you can play around with neural networks without um, after skipping all the faff of coding. Feel free to play around with the noise and batch size parameters, by the way. Something I found with the first task is if you set the activation function to linear, the model won't be able to determine high regions of curvature or non-linearity. The loss is always quite high when you set it to linear for some models. And if you scroll further down the web page, you'll hit the second exercise, which is called neural net initialization. And I had a quick go at it earlier, and it's again pretty interesting at looking at how you can initialize a neural network, starting with just the first layer and getting the relevant outputs. Um, what I noticed was whenever you add extra layers and extra nodes, um, the results are more repeatable. So on each run, the result model looks roughly the same. Um, yeah, so that's what I've noticed when you add extra layers and extra neurons. And the very last exercise is an interesting one because it plays around with the spiral data. Um, so that's worth looking into. Given the limited features you've got, how would you be able to recognize spiral curvature? It's also worth looking into whether you get a better model if you use additional features like the sine functions at the bottom, especially given the curvature and the shape of this data set. I just saw the question. In terms of batch size, um, I believe it means the number of batches of training data you supply to the model, but I'm not entirely sure. I'll get back to you on that. Right. So I think that's 10 minutes. So feel free to try the rest of it at home. What we've got here is a fun little exercise we can try out called limits of a neural network. So it's essentially a neural network where we can easily input data and see how it works out. So I'll try to screen share me playing this using some input files on my own computer. Right, so what we've got here is Teachable Machine. So in this experiment, we're going to use Teachable Machine, which is another online tool for machine learning powered by this organization called MobileNet. And it's essentially a neural network that's optimized for size, so it can run on your smartphone. So feel free to have a go at this whenever you're free. I'll put the link up in the chat when I'm done with this quick demo. Um, but essentially, if I can get it to work. So you can do different projects, image projects, audio projects, or standing in front of the camera and detecting which pose you're at. I think that's what they demoed here. Yeah. So just for the ease of prediction, I'm going to have a go at image projects, and you can upload some files from your computer. So I'll try that. So I put up 3 images of lions into class 1. I was tired of cats and dogs. And into class 2, I'll add in 3 images of tigers. So again, color-wise, the image RGB values are pretty similar, but it's whether or not the model can learn how to detect stripes. So we let our model train. So it's training with the set of 6 images. So I won't be expecting a very high model. And now we can input a test data either using webcam or a file. So if I just put in an image file of another lion, let's see what it classes it as. So I put in this image file and it's clearly a lion, and it said, right, it's class 1. Class 1 was our lion class. I'll change the names. So that worked. If we try a different image, now I'm going to give a curveball at this. I'm going to put in a white tiger and see what it says, because a white tiger is clearly an exception from the typical tigers we put in so far. It still managed to classify it as a tiger, class 2. I think the giveaway was the stripes and maybe the lack of a mane. But yeah, so that's pretty interesting because I didn't try it with a white tiger. I wanted to see what would happen. So yeah, that was fun. Yeah, you can also train it with pictures of yourself and see if it can recognize you from your webcam. So that's a fun exercise to try at home or with friends. If I just stop sharing this, get back to right. So I'll put up the link for this in the chat so you can have a play around with it. But other than that, that brings us to the end of this session. So some of the questions worth reviewing are revisiting what a neural network is, when is a neural network useful as opposed to traditional programming or just a simple machine learning model. The main thing to take away about this is neural networks are essentially a bunch of machine learning models layered one after another. And what can you do? What can it do that a simple model might not be able to do? So in terms of the sort of data it can handle, and what is a limitation of a neural network or just machine learning in general? So those are some questions worth pondering. But yeah, thank you everyone for coming. And it was really fun and engaging to present it. I hope you had just as much fun watching this presentation as I had going through it. And yeah, in 2 weeks' time, we'll be moving on to the 3rd session, which is the final session of the beginner track. After that, we can move on to the intermediate track, where we'll be diving a bit more into TensorFlow and coding solutions itself. So while TensorFlow Playground was fun and all, it's always fun to see what you guys can come up with. So thank you everyone for coming.